Hi, I'm Madhumita Anandan. I'm a graduate student with the Department of Electrical and Computer Engineering at the University of Florida. This is a presentation of the project prototype of my project in partial fulfillment of the course EEL 6825 pattern recognition for the spring 2017 semester. The project is vehicle driver eye state recognition using deep learning. The presentation will discuss the following topics: the objective of the project, the actual proposal, existing work in this area, the implementation steps of the prototype, the future scope for this project, conclusion and summary, and references. The main objective of this project is to use deep learning algorithms to come up with a method to classify eyes as closed or open, that is eye state detection using deep learning algorithm. This is because daily lives of people involves a lot of public and private transport. This involves a lot of people driving vehicles, and the cause of accidents is carelessness behind the wheel or falling asleep behind the wheel. This can be overcome by providing proper driver assistant, wherein a particular module continuously monitors the driver's eye state to see if they're open or closed. If the eyes remain closed for more than a particular amount of time, an alert could be triggered to alert both the drivers and neighboring vehicles. The proposal, as stated in the previous slide, involves use of deep learning methods to classify detected eyes as either open or closed. Weiler-Jones face detection algorithm, which uses Haar cascades, was used for face recognition and eye recognition task. The pictures in the slide show a subset of open eye and closed eye images in the training set. The training set is composed of a set of cropped and resized images of the eyes from AT&T indoor faces dataset, faces in the wild dataset, and my own eye images. There is existing work in the field of eye state recognition, but there isn't much literature on the use of deep learning methods to accomplish the same task. One of the first methods is the use of Weiler-Jones face detection algorithm. As known that Weiler-Jones face detection algorithm can only detect open eyes and not closed eyes. The fact of eyes not being detected was used as a decision criterion in defining eye state in the first method, which is not the right approach as no classification is actually done. There are other machine learning techniques like linear binary patterns and support vector machines that were used for eye state classification. And this is explained by the point 2 in the slide. There are a few papers on the use of core image processing techniques like edge detection and generalized Huff transform for the detection of eyes. This is discussed by the third bullet point. The project implementation, the flow of the presentation will be as follows. First will be an introduction and contrasting of how machine learning, deep learning, and artificial intelligence differ from each other, and working on an artificial neuron. Then the second part would discuss the working of a Weiler-Jones face detection algorithm and its use in detection of face and eyes. It is followed by a discussion on data pre-processing, which constitutes an important element of any machine learning algorithm. This is followed by a brief explanation of the two types of neural networks used in this case, multi-layer perceptron and a convolutional neural network. Artificial intelligence, machine learning and deep learning. all perform the same task of autonomous decision making, but the approaches are different. Artificial intelligence uses a set of rules or logic to separate data in the real world. It works by using rule based trees called ontologies, which acts like a dictionary of various actions and decisions based on which a decision is taken. Unfortunately, real world data includes a lot of ambiguity and highly non-linear, so rules like this cannot effectively separate such data. Machine learning algorithms, on the other hand, unlike AI, instead of forming rules and applying it on the data, learns the various rules and boundaries from the data. It uses statistical methods to classify, predict, or generate data. Machine learning algorithms can be of different types. They can be either parametric or non-parametric. Parametric algorithms involve use of hyperparameters, just like in a neural network, where parameters like learning rate, number of neurons, etc. has to be adjusted. Non-parametric techniques have minimal or no hyperparameters for adjustment, just like a random forest or a dendrogram diagram. A supervised machine learning algorithm involves labeled input or training data, whereas an unsupervised algorithm involves unlabeled data and is more desirable for real world applications. Machine learning algorithms can also be linear or non-linear. A linear algorithm just works by forming a weighted linear combination of inputs and can form only linear decision boundaries, whereas a non-linear decision boundary can be formed by non-linear machine learning algorithms. A machine learning algorithm can also act as a classifier for insertion of decision boundaries, a predictor to predict future signals in case of a voice signal, or a generator to back propagate from the features to the input. In case of algorithms like the restricted Boltzmann machine, the slide contains a picture of a supervised machine learning model where the training set is a set of text documents or images from which features are extracted, and the features and labels are learned by the machine learning algorithm. Whenever a new input sample comes in, the same feature extraction algorithm is used to extract the feature vector to perform a predictive analysis of the input and output. Deep learning models the working of the human brain, where a macula Pitts neuron models the human brain, wherein various neurons are connected by nerve sheaths and neurotransmitters are used to transmit electric signals from each neuron whenever the data at a particular neuron exceeds a particular threshold. In case of a Macula-Pitts model, a weighted linear combination of inputs called a net is applied to a neuron, which in turn applies a non-linear activation function on this net to form a non-linear decision boundary. A special weight called bias is also added to the neuron, which controls the intercept or position of the decision boundary. These perceptrons are the key elements of the hidden layers of the neural network. A neural network usually consists of an input layer, a number of hidden layers, and output layers. Such nonlinear neurons are usually present in the hidden and the output layers. Video acquisition and face and eye detection. Video acquisition in the real product can be either done using a USB or a wireless camera. For the case of this demo, laptop's web cameras was used as the video acquisition medium. Viola-Jones face detection algorithm was used to perform face and eye detection. Viola-Jones face detection algorithm is based on three main steps: integral image formation, feature selection, and boosting. an attentional cascade to quickly remove non-eyes and non-faces. An integral image can be calculated quickly at one pass of an image by calculating pixel value of at each pixel by the addition of all pixels above and to the left of that particular pixel. Whenever a particular image region has to be retrieved from this integral image, a rectangle is chosen around that area, and the integral image values at the corners of that rectangle are used to retrieve the image values in that region. Feature selection is done using special windows called Haar features, which are either a rectangle or square windows with black and white regions. The black regions act as marks, whereas white regions are used for feature extraction. These Haar windows are used for selection of weak features from the image and constitute weak classifiers. In the attentional cascade state, these weak classifiers are combined to form strong classifiers. In attentional cascade stage, a number of strong classifiers are cascaded one after the other for quick rejection of non-face and non-eyes images. Data pre-processing. Data pre-processing plays an important role in any machine learning algorithm. It is mainly used to reduce the dimensionality of data, to overcome the curse of dimensionality, scale the data to fit our model, and so on. In the case of multi-layer perceptron, a variance ratio plot was used to find that most of the differences were captured in the first 10 principal components, and the input image was dimensionality reduced to a 10 cross 10 image, flattened and fed as input to an MLP. The data was also scaled by division by 255 so as to promote fast convergence and to avoid saturation of neurons. In case of a convolutional neural net, the convolutional layers directly act on the 2D image to extract meaningful features, and so the original grayscale image of dimension 135/50 was given as input to the CNN. This slide explains the architecture of the multi-layer perceptron. The learning was carried out using an RMS propagation based optimizer wherein adaptive step sizes were used. It can be seen that the validation loss goes up after about 30 iteration. So this criterion was used for early stopping. Here, the number of input nodes corresponds to the dimensionality of the data. That is, the 10 cross 10 in this case does 100. The number of output nodes corresponds to the number of classes. That is 2. Here, one hidden layer, use of one hidden layer with the number of processing elements gave only low accuracies of around 60%. Addition of another hidden layer brought up the accuracy to 76%. In order to avoid overfitting, a dropout of 0.2% was used. The activation function used as the output layer was softmax, as it models the evidences of data into a probability distribution for easier visualization. The activation function is the hidden rectilinear activation function. This is because this has a higher dynamic range and less possibility for neuron saturation. This shows an accuracy plot and confusion matrix of a multi-layer perceptron. The maximum accuracy achieved on the validation dataset using an MLP of the discussed architecture is 76.2%. The confusion matrix shows that most of the data is correctly classified, giving rise to a high number of true positives and true negatives, and a few also fall in the false positives and false negative category. A convolutional neural network was fed with an original grayscale image of resolution 35/150 in case of testing, and multiple training images of the same resolution in the training phase. The architecture similarly contained the number of input nodes to the dense layer as 50 cross 135, the flattened images. The convolutional layer took the direct images as the input. For the convolutional layers, 3 cross 3 kernels were chosen by trial and error as they gave the highest accuracy. A dropout rate of 0.2 percentage was employed in this case. It can be seen that the learning curves are more jittery than an MLP due to the higher non-linearity involved in the CNN due to extraction of most discriminating features by the convolutional layers in a CNN. The validation loss goes up at a point, and this was used as a criterion to stop training for early stopping to avoid overfitting. The accuracy of CNN was slightly greater than the MLP, and it is at 80.25 percentage for the discussed architecture, and the confusion matrix is slightly better than that of an MLP. The future scope of this experiment can use other dimensionality reduction techniques like linear discriminant analysis or linear binary patterns. Use of a bigger database could yield better results. This prototype could be made into a dedicated application for driver high state detection. Thus, this prototype and proposal explored the use of deep learning algorithms for the application of I-state classification, as existing literature exists only for the use of machine learning and image processing techniques to perform the task. It was seen that CNN had better results than MLP but had higher training time due to computational complexity. So there exists a trade-off between the required accuracy, computational complexity, and the resources available. These are the references that helped me accomplish this project. Now I will go through the code for the same. The code was developed in Python using various image processing and machine learning libraries. The initial part of the code involves importing of various libraries. The MLP implementation used a batch size of 10, number of class of 2, and 100 epochs initially. This part of the code defines the network architecture where 2 hidden layers were used and the corresponding activation functions loss is used or visible here. It can be seen that the confusion matrix is almost similar as seen in the slides but differs on each run due to the difference of initial seed used for initialization of the weights. These are the dimensionality reduced images from the training set, the learning curve, and the accuracy plot. This function is used in the real-time demo wherein the learned weights from the MLP or the CNN are applied on the live captured iData to classify it as open or closed. This is the Weiler-Jones phase detection algorithm, which uses frontal, face, and eyes hair cascades to detect the face and eye regions. CNN has the same implementation except that it has various convolution and pooling layers before the features are fed into the dense layer. A CNN has better performance as seen than an MLP. These are the features that are extracted from the first layer of a CNN. Adding more convolution layers may extract more meaningful features. Since the eyes is a complex object, not all features are readable, human readable. Let me show a demo of the code. Face detection algorithm. It detects my let me run it again. Run off. Can be seen the Vilogen's face detection algorithm detects my eyes and face. It is not perfect as it sometimes also detects other objects. It can be seen that my eyes are open. If my eyes are closed for a particular period of time, the window will automatically exist and show me an alert message. Okay, let's look at the outputs. It can be seen that it detected most of my eye states correctly. Towards the end, my eyes remained closed, and since it was closed for more than a particular period, it gives an alert message asking me to wake up. Thanks for watching the video.